Welcome all. So today's session we will discuss about different types of semiconductors based on their band gaps. So before going to that, we just recall the what are important characteristics of semiconductors. All of you know semiconductors are substances having conductivity between conductors and insulators. So I just point out that point. Okay. Okay. So conductivity between conductors and insulators. And the second point is the resistivity ranges between 10 raised to 5, 10 raised to minus 5 ohm meter to 10 raised to 5 ohm meter. Okay. So resistivity ranges from 10 raised to minus 5 ohm meter to 10 raised to 5 ohm meter. Okay. And the third point is usually in the periodic table the semiconductors belong to the group 4. Okay, so it belongs to group 4, and usually we doing doping with the elements from group 3 and 5. Okay, or group 2 and 6 likewise. The band gap of semiconductors, that is the important thing we have to note down. Band gap of semiconductors is between 0.2 to 0.2 electron volt to 3 electron volt. Okay, 0.2 to 3 electron volt. This is the range. And usually the major parameter that we when studying the semiconductor, we note on the temperature. When we increase the temperature, there will be changes in the electrical and optical properties. The temperature coefficient of semiconductors is negative. Okay, for resistance of semiconductor, the temperature coefficient of resistance of semiconductors is negative. That is the major parameter that you have to note. So the temperature coefficient of resistance of semiconductor is negative. So these are the major parameters and main points that we have to recall before going to study the different properties, different classification of semiconductors based on band gap. So from here you can see the band gap is ranges between 0.2 electron volt to 3 electron volt. Based on this, the semiconductors are divided into two. So based on band gap, semiconductors divided into two. So first one is direct band gap semiconductors. Direct band gap semiconductors. And the second one is indirect band gap semiconductors. So in the next session we will discuss detail about direct bandgap and indirect bandgap semiconductors. Okay. So in this picture I just drawing the direct bandgap and indirect bandgap semiconductors. This is the EK diagram of conduction band and the valence band I have drawn here. So this one is the valence band, okay, and this one is the conduction band. And you can see this point is called valence band edge and this point is called conduction band edge. So I just marked down it. This point is called valence band edge and this point is called conduction band edge. And here it will be EK diagram. This y-axis denotes the energy level and the x-axis denotes the vector k vector. Okay, so that I have drawn here. So this is for direct band gap. Semiconductor, and this picture is for indirect band gap semiconductor. Okay, so here this is also called valence band edge, and here you can see there is no conduction band edge, but conduction band edge is not here. It's moved to some another point. So this is the conduction band edge. Okay. So from this picture itself you can understood what is the difference between direct band gap and indirect band gap semiconductors. So in the direct band gap semiconductors we can see the minimum of the conduction band, that is this point, conduction band edge. Okay, minimum of the conduction band and the maximum of the valence band, maximum point of valence band, this point. Okay, so the maximum of the valence band occur at the same value of the wave vector. So this is the wave vector point k equal to 0, that is zone center. We usually say it as zone center. Okay, or k equal to 0. So wave vector exactly the same point we can see the minimum of the conduction band edge and the maximum of the valence band edge. So these points will occur at the same point at direct band gap semiconductors. Hence when photon is absorbed, okay, so when a material is absorbed some photon of energy h nu, okay, you can see one electron from here is just moved to from the zone center, just move to directly to the conduction band. Okay, so when a photon is absorbed, the electron is excited from the valence band to the conduction band. Okay, that you can see here. So it is just moved to conduction band. So I will draw here the electron. Okay, this is hole now, and I will show one arrow here. So the electron in the valence band is excited to conduction band now, that you can see. So here you can see there is no change in k vector. Exactly which position is in electron in the k position. If it is here, it is go directly to excited to this point. Okay, so there is no change in k vector, exactly to the same position. So the photon wave vector is here negligibly small. We can say there is no change in vector. So we can avoid that. If there is any light change also, we can consider it as negligible. Okay, so the transition here you can see is the direct transition or vertical transition, correspond to EK diagram. Okay, so in the direct bandgap semiconductor you can see the zone center, the two wave vectors or two edges coming in at the same position of wave vector. So the transition is, vertical transition is very direct. So you can call it as a direct bandgap semiconductor. The example for direct bandgap semiconductors are, materials are gallium arsenide. Examples, okay, gallium arsenide and cadmium terbium. Okay, so these are the examples. You can see here these materials are only we get these materials by using and these are not pure semiconductors. All these are we get these semiconductors using doping only. Okay, so these are extrinsic semiconductors where we can see the direct band gaps. Okay, next one is the indirect bandgap semiconductors. From the picture you can see the two edges are not in the same position. That means in the zone center, not in the same position. So when we when there is one electron here, it is excited to this position. We can see we have to it have to go to the conduction band edge, but it when we do any transition, we can see that it have to move to this position. First it will come to here and then move to this position. Okay, so I will just draw that points. Okay, from here up to here it will move, and I will draw that to single. Okay, and here you can see it will again move to this position. That will also we will draw. Okay, so it have to move to this position. Okay, so first it have to come to here and then it will move to this position. So when if there is some photon is if there is any photon came to the indirect bandgap semiconductor, you can see it will only move to first position. Then we need some other wave vector transitions. That is it. The wave vector is not exactly in the same position, so we need some vibrations that usually we call phonons. Okay, we need the help of phonons, then only this can move to the conduction band edge. So here we can do the direct transition, but in the case of indirect bandgap materials, the zone centers are not the conduction band edges and valence band edges not at the zone center. So we need the there is some changes for wave vector. So the wave vector difference can be balanced by using phonons. Okay, phonons means the absorption or emission of lattice vibrations that is quantized as phonons. Okay, so here we can write it as Kc will be approximately equal to Kv plus K photon. Okay, Kc means the wave vector position of conduction band, which will be equal to wave vector position of valence band, plus K photon means we need the wave vector. There is a small wave vector for photon also that we need for this small change. Okay, so we can move this or we can excite this electron to conduction band change then only. Okay, so from this picture you can understand what will be the difference in direct and the indirect bandgap semiconductors. The main point you have to write in 1 mark, that is the zone center is not in same for the direct bandgap semiconductors. The conduction band edge is placed in some other point. Okay, so there is substantial wave vector changes you can see here. Here there is the conduction band edge, minimum of conduction band edge and maximum of valence band edge is at the same point. So but here you can see there is some substantial changes. Okay, so there is no direct transition possible in the case of indirect bandgap semiconductors. These are the points that you have to remember while writing the answer. Okay. Next we will discuss about the light emitting diode. Okay. Light emitting diode, or we call it as LED. Light emitting diode. So in light emitting diode, I draw a picture here. You can see there is a PN junction, and when the light is fall into the when we forwarded the connection, okay, when we give any forward biased this PN junction, what will happen to this PN junction? All the electrons in the conduction band will recombine to valence band, okay, and it will produce photons that is drawn here. Okay, these photons we will usually see as light produced from that PN junction. Okay, so this effect we usually call it as electroluminescence. So when PN junction is forwarded biased, that you can see here, when the PN junction is forwarded biased, what will happen? When the electrons and holes are able to cross the junction and are able to recombine with the opposite charges carriers in the device, okay, releasing energy. So the energy release will be in the form of photons. So we can see that there will be some light produced from that object. Okay, so all of you saw the LED glowing. Okay, when we apply some current to that LED, what will happen? It will glow. Okay, so that glowing means it have some produced some energy from that photons. We can see it as a light glowing from that LED. Okay, so this is the basic principle of light emitting diode. So during usually the color of light emitted is decided by the band gap energy of the semiconductor. That is the important thing. You can usually you saw many colored LEDs in the lab, red, green, white, etc. So the light the color is occurred because of the band gap energy. The band gap energy decides the color of the light. Okay, and during the recombination, the electrons in the conduction band move down to the valence band. When the electrons move from the conduction band to the valence band, the electrons emit energy in the form of photons that is drawn here. Okay, you can see electrons already when we this is some kind of direct bandgap semiconductors. Actually here this light emitting diode, all the materials will be let me write gallium arsenide, all the materials are made by gallium arsenide materials. So you can see the light emitting diode is LEDs are some examples of direct bandgap semiconductors. So in direct bandgap semiconductors, you can you already know the conduction band minimum and valence band maximum are in the same position. Okay, so the direct transition or vertical transitions are possible there. So when we give some forward bias to this gallium arsenide material, what will happen? the already excited position excited electrons in which will be in the conduction band will move to valence band, and that is it recombine to valence band, and it will produce photons. As much photons it absorb, it will emit that photons, and that photons will be coming and that we see as light, okay, in the form of light. That is the basic principle of light emitting diode. Okay. Next is photodiode. Photodiode is nothing but it's similar to LED, but here actually it absorbs the light or photons and it photodiode actually is a PN junction diode, so that is commonly used as a light detector. Okay, so it absorbs light and it will generate some current according to that particular light. So the diode converts light into electric current, just opposite LED in which we are applied some current and we will generate not the LEDs convert that current into photons in the form of photons. Here it will absorb the photons or light and it will generate some current according to that particular light. Okay, the same the principle is exactly the same. There is some PN junction here, and what will happen when the diode when a photon of energy is greater than the band gap energy of semiconductor is incident, it is absorbed to photogenerate or electron hole pair. So the light is absorbed by this electron hole pair. If the photon absorption occurs in the depletion region, the carriers are drifted to the opposite direction. So if it absorbs in this position, what will happen? The carriers, you can see here electrons and holes are there, so it will drifted to on the different direction. Okay, so this drifting will built in the electric field of junction, so we can get creating a photo current in the external circuit. So we will get some current into the external circuit. This is the basic principle of photodiodes. So hope you understood these things. Thank you.